Go. Oops. Oh, I did that. That's not what I wanted to do. All right. So I want you to work on some homework problems, of course.
Wow.
Oh, this is homework?
Yes.
Oh my god.
Is.
Killing me.
Wow.
Write this down.
Today is the same time, gosh. I want to do it all.
I'm giving you a week to do it.
Yeah, but you know I'm not gonna do it.
That's not true. I don't do that.
Not proud.
You guys can play more about homework, I tell you. It's not a lot.
It's a lot.
It's not a lot. That's 12 problems.
That's a lot.
How is that a lot? 12 problems, 7 days. Fewer than 2 problems a day. Less than 2 problems a day.
If you do it.
Why aren't you working on math every day?
Because I'm in class with it.
Because like days like today, I will not do this.
Well, then that's your problem.
It's your problem.
It's not my problem.
Making me do these classes.
You realize if you don't turn in homework, that's less work for me. So it's really not my problem.
Is the last line from the book?
It's the last one from the book.
Okay. What book?
Yeah, we have a textbook.
Oh, the statistical one?
You know, the same book where all the odd problems are, though the answers are posted on Moodle, that same textbook.
But these aren't
Don't
all.
know your mark.
You know, full worked out solutions that I typed up this summer, you know, in preparation for this class. Which means there are probably typos in there, but you know. All right. Well, of course you're not ready. Why would I expect you to be?
You're making me write down a bunch of problems.
You know, you'd probably write them down faster if you weren't whining about having to do them.
I've actually been writing this time.
I've been writing this whole time that we've been talking about it.
I said you would write them down faster. I didn't say you weren't writing.
I don't think I write them fast.
Not sure what that is.
I don't think that.
I'm pretty sure it is how it works, because you're thinking about whining rather than what you're doing. All right. So last time we talked about binomial distribution.
Good job.
Sometimes I don't. Remember that our PMF looks like that. And then your x goes from 0 to n. So again, the idea behind, the idea behind the binomial distribution is we have those independent and identical trials with 2 possible outcomes. We call those Bernoulli trials, where you've got a success and a failure. And what the binomial distribution is counting the number of successes that pop up. That's what we're counting. That's what the x represents. We haven't mentioned this word before, so I'll mention it now. Where your probability mass function, and later on when we talk about probability density function, where that's non-zero is what's referred to as the support. So this would be the support of your random variable. So again, the support is just the x values for which your probability mass function, or later on when you do continuous distributions, your probability density function is non-zero. At the end of class last time, we figured out what the mean of this distribution is. What was the mean again? NP. And then in a similar fashion to what we did last time, I'm not going to go through it. You can also figure out the variance. The variance, and part of the variance has NP in it, and it's also times the 1 minus P. The way you actually do this, like I said, it's very, very similar to how we did the mean when we had to multiply by x and then re-index the series so that we could add it up and then see the piece that had the probability, a different PMF in it that added to 1. You do a similar fashion, and another trick that you can do for calculating variance. Remember we did expected value of x squared minus expected value of x quantity squared? There's another way to get at it. If we do expected value of x times x minus 1, this would be expected value of x squared minus x. So this would be expected value of x squared and then minus an expected value of x. So to finish off the formula, we need to add back the expected value of x, or the mean, and subtract off the mean squared. So this is another way that you can calculate variance. If you were doing that for the binomial distribution, this is the way you would want to do it. And the reason for that is, remember when we took the expected value, the x canceled with the x and the x factorial. We broke up the n choose x in its formula. Right, we took the x on top and canceled with one of the x's on bottom and left it with x minus 1 factorial. If I do x times x minus 1, then I will get another cancellation and we'll be left with an x minus 2 factorial. That's why that's there. Again, that was more of just informational purposes. They do this in the text, Grace, the textbook, the textbook that we have for this class.
I'm pretty sure I have.
They do this in the text on page 84. So the derivation for that's on page 84 if you're interested in looking at it. All right, so I want to do an example or two more here with the binomial distribution before we talk about some new stuff today, about old stuff with new stuff. So let's look at, this is 19.5 in the handout that I gave out last time. Yes.
The calculation for variance on the right is just like another.
It's another way that you can calculate the variance, right?
So that's just a simplified version of that.
No, this is, if you use this is a general formula. This is specific to the binomial distribution. This is just another way that you can calculate the variance for any distribution. The reason why we like it for the binomial distribution is because, again, like I was mentioning, when you do that n choose x, there's an x factorial in the denominator. This will cancel an x and an x minus 1 in that x factorial. That's why.
Can you say one more time about this one?
This one? This is the variance for any binomial. So you know the number of trials and you know the probability of success. The one that I boxed is just a general formula. All right, so and it's a 19.5. It says a box contains 10 balls, 3 red, 2 yellow, and 5 blue. Oops. And it says five balls are selected without with replacement. So what, again, with replacement means what? Yeah, you pull one out, you put it back in, you pull a second one out, you put it back in, pull a third one out, put it back in, pull a fourth one out, back in, fifth one out, back in. So then it asks us to find the probability. That was really weird. Not sure why I did that. I think it's probably because we're just pulling it down. There we go. All right, so this one asks us to find the probability that fewer than 2 of the balls are red. So what does fewer than 2 mean? 0 or 1, but not 2, right? So could be 0, could be 1. But not 2 or more, right? Fewer than, so not less than or equal to. All right, so we need the probability that we have no red balls selected or only one red ball selected. What about this is telling us that it's binomial? Now for binomial, again, remember we have to have independent and identical trials in which there are only 2 possible outcomes, right? Why are they independent? Why are the trials independent here? What are we doing? It's because it's with replacement, right? You pull a ball out, you put it back in. Pull a ball out, put it back in. That's why it's independent, right? And why it's identical. If we were to do this without replacement, it would not be a binomial trial, right? A Bernoulli trial, I should say. Binomial. The other thing that we also need is 2 possible outcomes. What are your 2 outcomes in this case? Yeah, red or not red, right? Those are going to be your 2 possible outcomes, correct? Because all we're doing is trying to count the number that are red. So it's independent and identical because they're being selected with replacement, and it's 2 possible outcomes because all we're interested in this case is red or not red. All right. So if success is drawing a red ball, what's your p-value? Three-tenths? Right? 3 out of 10? Okay. What is n? How many trials are you doing? 5. Good. All right. So these are the 2 important, what we typically refer to as parameters for a binomial distribution. You need to know the number of trials. You need to know the number of successes. So if x is counting the number of red balls here, we say that x is a binomial on 5 trials with a probability of success of 3/10, or we would write the notation. We use little b to denote that we're doing a binomial random variable. The number of trials comes first, and the probability would come second. So this is just our notation for that, right? So again, the b is standing for binomial. The 5 is the number of trials, and the 3/10 is the probability of success. Again, once we know the number of trials and the probability of success, if we know it's a binomial random variable, we know the entire distribution because we know it's PMF. All right, so we just said that we wanted the probability of 0 or 1. So the probability that x is less than 2, fewer than 2, will be the probability that it's 0 or 1. And then we just use our PMF, right? So what will we get for doing probability that x is equal to 0?
Okay.
times e to the 0 power
Okay, so 3/10 to the 0.
times quantity 1 minus 3/10
Okay.
0.
To the be 5 minus 0, right? Because that part's n minus x. Oops, I wrote the wrong thing up here. This should be n minus x. That was my problem. Sam. So that's for x equal to 0, and it looks similar for x equal to 1, right? We agree? So then at this point, it would be a matter of putting it into your calculator and figuring out what the final answer is. Did you agree? 5282. Hey, look at that. It was one of the answers, too. What do you know about that? We're on the sheet that I gave out last time. Thanks. Questions on this one? All right, let's go back to the beginning here where we said, what if it said, we noticed it said with replacement. What if it said without replacement? If you selected 5 balls without replacement, is that binomial anymore? No. Right? And because the probability of success would change from trial to trial, because the number of balls left in the box is going down if you do it without replacement, right? So if we wanted, say, the probability that x is less than 2, so right now I'll say suppose we draw without replacement. Then we would have, let's think about what the PMF would be, generally. You would have 10 balls to choose from, and we're choosing 5, right? That's without replacement, isn't it? Correct? We know that 3 of them are red, and we're going to choose X of those. And the rest have to be not red. So we would choose from the not red piece, the 10 minus 3, that's why I wrote the 10 minus 3 there. And then the rest, so up to 5, we have the 5 minus X, right? These choose the red balls, these choose the non-red balls. Now I wrote it like this because I'm trying to think of a more general formula for this as we go along. I keep forgetting to lay this flat, sorry. So we want to come up with a more general formula for this. So this is the number of items that we select from that we want. This is how many we're going to get. This is the leftover, right? And this is how many of the rest we'll pick. And then this is the total number of selections. And in this case, our support, what the possible x's can be, are from 0 to 3, right? All right, this type of distribution, this is an example of a hypergeometric distribution. Notice that the problem was similar, right? It looks like the binomial problem. All I did was just change with to without. And then I get a hypergeometric distribution instead. So they're very, very close to each other. In fact, if your size of the whole thing, so let's get what I'm talking about, the 10, if that size is really, really, really big, it might as well be a binomial distribution. Because it's going to be that close together. And the reason for that is, if this is really, 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 really big, and this is small relative to that, then this is also really, really big and close to this, and basically you get 1. Is what essentially happens. It's along those lines. So for a general hypergeometric distribution, you have n objects and there's 2 different types. So 2 distinct groups of objects. There's n total. There's n1 objects of the first type. I'll just say type 1 for lack of a better one, that better word. And you're going to make selections of size, what's the letter they use in the books, just so I don't mess that up. Oh, they say X. So, selections of size X, or no, selections of size, they use a capital N, sorry. They use a capital N for this one. Sorry. I just want to make sure that it looks like what you see in the book when I go back and look at it. Because again, these are the ones that I don't want you to memorize. So you'll reproduce them on test. So I want to make sure I want to use the same letters. All right. So I got N total, capital N total objects, N1 objects of type 1, selections of size N. Okay. And we're going to choose X objects, of type 1. All right, so your PMF, if we use that same formula we had, overall, you're going to choose, out of capital N total, you're going to choose little n. Right? Again, this is total number of objects. This is how many you're selecting. Right? Total number, how many you're selecting. You're going to choose, out of the objects of type 1, you're going to choose X. And out of the objects of the other type, you're going to choose N minus X. That was why I wrote that one with the numbers in it a little bit funkier. Okay. Some of them are of the first type, the rest are of the second type. This is why I'm saying that it kind of looks binomial, right? You've got 2 separate, mutually exclusive groups of things, right? Some of type 1, some of type 2. Okay? The difference is that you're not doing independent and identical trials. These are when you're selecting things without replacement, so that things are changing slightly as you go. Okay? But this is your PMF, your X values. Your X has to be, of course, less than what you're selecting, the total number you select. But it also has to be less than or equal to N1. And you also need that when you do N minus X, it to be less than or equal to N minus little n1. Though, otherwise, these don't make sense, right? I can't select more things of the first type than I have things that I'm selecting total. Right? I can't select more things of the first type than I have things of the first type. And I can't select more things of the second type than I have things of the second type. That's what those 3 conditions are saying. I can't select more things than I have to select from, or I'm sorry, that I'm selecting. And then I can't select too many of type 1 or too many of type 2 if I run out. All right, I'm not. This is another one of these. I'm not going to run through the derivation of these, but you can show that the mean of this is, pardon me, it's little n times little n1 over capital N. This is another way that looks like a binomial. What was the mean for the binomial distribution again? NP, right? It's probability of success. If we were doing this with identical trials with replacement, N1 over capital N is P, right? That's how we got the 3/10, isn't it? Right? So this is another way it looks like it's a binomial. The variance is where it pops up that's funky. This variance is really funky. It looks like N times P times 1 minus P. This is what that would look like. Right? And then we have one more, but this isn't it. But this looks like your N, this looks like your P. This looks like 1 minus P, doesn't it? Okay. The last piece is what's different. The capital N minus little n over capital N minus 1. So this is why I said that as your number of things that you're choosing from is big relative to the number of things that you're choosing, it might as well be binomial. Because if capital N is really, really big relative to little n, what is this fraction close to? Think about it this way. If this is 1,000,000 and this is 5, so you've got 999,995 over 999,999. What's that really close to? 1, right? So if capital N is big relative to little n, you might as well use binomial. Because it's essentially the same thing.
What's the regular N?
This one?
Yeah.
That's the number of things that you're selecting overall. So that was like the 5 in the problem.
Sam, so if we were to use the binomial distribution as an approximation, would it be an approximation?
It'd be an approximation, yeah. Yep. And if it's really close, it's a really good approximation. All right. So that's hypergeometric. We've done problems that were hypergeometric distributions. We just didn't call it that, right? We've done problems where we've selected a certain number of type 1 and the rest are type 2. Same.
So what would for 19, the one we just did, would it just be 1.5?
Yeah, it would be 5 times 3/10, so 1.5. Yeah, that's right. All right, let's do one more with binomial, and then we'll go on to the next topic. Let's do 19.7. Give me a second to read it. All right, so this is
well, it's probably a binomial distribution problem since it's in a section titled binomial distribution. And otherwise you'd be violating the 11th commandment of thou shalt use the nature theorem in the section to do all problems following that section. It's a lesser known commandment.
It's spoken.
It's an unspoken commandment. All right. So what about this problem tells you that it's going to be binomial?
Probabilities that
Okay, so it says independent, right? It even tells you the probability that a passenger will not show up is 0.1 independent of other passengers, right? So we already have independent, right? And what is it we're trying to count? Yeah, how many people show up, right?
Do they actually do that?
Oversell? Oh yeah.
So what happens?
They ask people to step off, and that's why they give them monetary incentives.
Facebook videos of those guys going crazy when they ask, get off the plane. There's a whole lawsuit.
I'd be so pissed.
No, they usually
I would just say no. I'd be like, no.
they usually ask for volunteers and then they'll like give you some kind of compensation for it.
Yeah, we got asked. Dr. Stickles and I got asked to take the next flight out of Bloomington. So they gave us $800 of vouchers for flying later, and we got first class. So that worked out okay.
Okay, that works out well.
That worked out really well. So and it just got us there like 4 hours later.
I'm pretty sure they usually choose, like, if you're a single person flying, they usually ask a single person or couples, not families.
Yeah, usually, yeah.
But doesn't that just like put the next plane at risk for also being?
Yeah. Oh yeah. That's why you get these announcements all over the airport.
What announcement?
Yeah. There's all sorts of announcements like that, but yeah, they'll ask people that it's oversold and we need to ask for volunteers to step off, and
It's just how it goes.
it's just how it goes, Grace.
Well,
Why don't you just
sell
fly
them
more?
first, like they wouldn't have that problem.
They make more money by selling those.
Money.
Yeah, it's money is what it's about.
Actuaries do that, right?
Follow the money trail.
Actuaries.
Mhm. They figure out these things. Why do you think we're studying this stuff as far as this goes?
I don't want to do this.
Okay. All right. Anyway, so what is it we're trying to count here?
The number of people who show up.
Number of people who show up, right? What's the problem? How many people show up when it becomes a problem? 31 or 32, right? So we want the probability that x is 31 or the probability that x is 32, right? Because that would give us the probability that more passengers show up than there are seats, correct? Which is no bueno, I agree. All right. So what's n in this case? Because we already established it was binomial. What's n in this case? 32, right? 30 is the number of seats that are available. 32 is your n. What's your p? What's the probability that somebody shows up? 0.9, right? I mean, you could have done it the other way. You could also do the probability of x is 0 or x is 1 and use that as the no-shows. There were no no-shows or there was one no-show. That's the same. You'll get the same answer. So what does the formula look like then? What will we plug in for probability that x is 31?
So 0.9.
So 32, choose 31. And then 0.9 to the power. 31, right? And then what's next? Yeah, 0.1 to the first, yeah. Right? Because remember, it's x and n minus x here. These numbers should always add up to n, by the way. These exponents should always add up to what n is. Because we're doing that many independent trials, right?
think about what the pieces mean. This is, I had 31 people show up and 1 not show up. And this is just the number of reorderings of how that can happen. What about for x visit 32? What would that look like? 32 choose 32. 0.9 to the 32. And 0.1 to the 0. Now, I wouldn't have to write this down every time because what is 32 choose 32 or n choose n? No matter what. 1. And anything to the 0 power, 1. Besides 0 to the 0 power, you don't know what that is. 0 to the 0 is undefined. No, you won't. All right. Anybody do that?
Yeah.
What'd you get?
0.1564.
0.1564? Okay. So 15% of the time somebody's going to be ticked off?
That seems high.
Yeah, it does. All right. Questions on that one? All right. So let's talk about another concept. This is referred to as the moment generating function. And then we're going to talk about a couple of other distributions in the midst of talking about moment generating function. All right, so here's the idea behind the moment generating function. Remember, the moments are your expected value of x to a power. Those are what we refer to as the moments, right? So the way that we get the moment generating function is the following. We think, usually don't use an F, usually we use a capital M. So the moment generating function is a function of some variable. The way we calculate the function is that we do the expected value of e to the tx. So this would be your sum over the whole support of e to the tx, f of x. This is weird, I know. Okay? What's that? Let's say it one more time. Sorry.
What's the TX?
The tx is the exponent. The x is the same x. The t is just another variable. We're going to talk about how it's used here in a second. I know this looks weird. Okay? I agree with you. It's weird. Okay? The idea here is to be able to use this to generate moments. In particular, to be able to generate how to get your mean and how to get your variance from this function. Okay. So one of the reasons why we use, yeah, Grace.
So if you were gonna plug something in as t, would that be like x squared, like as moment 2, or like what would it?
If you were going to plug in something for t, you literally plug the number in here. It's independent of what that x is. It's a function of two variables, t and x.
So what's t?
It's a variable.
Oh, I got that, but like what does it represent?
It's a variable.
Okay.
It represents a variable. If you would give me a minute. All right. So, distracted me now. This particular function is going to be used to generate the moment. So to be able to generate expected value of x, to be able to generate expected value of x squared, and so on down the line. Well, how would we get that? Well, let's just think about our function here, e to the tx, or just e to a power in general. What do you get when you differentiate e to a power? E to that power, right? And then times the derivative of the power, correct? So if I differentiate this thing with just don't worry about the parentheses, just e to the tx. If I differentiate that with respect to t, what do I get? I get x times e to the tx, right? If I differentiate it twice with respect to e, what do I get? X squared e to the tx. If I differentiate it 3 times with respect to t, what do I get? X cubed e to the tx. That's what the t is for. It's to help us get these derivatives with respect to that power. Okay? So anytime that we differentiate this with respect to t, an x pops out, right? Notice that we would have the same thing over here that pops out here and pops out here too, right? I would have, if I differentiate this, different derivatives behave nicely with respect to sum, so I can differentiate piece by piece. And remember again, we're differentiating with respect to the t, not the x. As far as the t is concerned, the x is constant, right? So I would have x, I would have x squared, I would have x cubed, getting the expected values that I want, but I still have that extra e to the tx in there. I want that to go away if I really want the expected value of x or x squared. What can I plug in for t to make this go away? 0, right? They'll make it a 1, correct? So that's how we get it. If you do the nth derivative and evaluate it at 0, that's going to be the expected value of x to the n. That's what we're using the variable for. It's literally to generate those powers and then we plug in the 0.
So a whole bunch of nothing.
Well, the other thing that the moment generating function does, which is more advanced than what we're going to talk about for our purposes, the moment generating function completely determines the distribution. So if you can recognize what the moment generating function is, what the form of it is, then you can tell what the distribution is. That proof of that's more advanced than what we're going to do, but we are actually going to use that fact several times throughout this semester and next. But the moment generating function also completely determines what the distribution is. It's not too hard to figure out why. If I know the moment generating function, I essentially know the PDF. It's sitting there at the coefficients on these e to the tx's, right? So if I know what the moment generating function is, I know what these coefficients are. So I know the PMF, so I know the distribution. That's the intuitive argument for why the moment generating function tells you what the distribution is. So in this case, let's look at a specific problem. Let's say we look at number 27.5. So that's on the single sheet that I handed out at the beginning of class. They give you the moment generating function to make sure that your moment generating function actually really does determine the whole distribution. You have to make sure that the moment generating function exists somewhere else besides 0. That if I plug in a number other than 0 for t for some other number, it actually still gives you something. The function actually exists. That's why it says for t less than 1 here, that little extra condition. It's just telling you that it really does exist for something else besides just 0. It's a technical detail for the later stuff.
Technicality.
It's a technical detail. You don't have to, for what we're going to do, we don't have to worry about it. Okay? All right. So this one asks us to find expected value of x cubed. So to find expected value of x cubed, how many derivatives am I going to have to take? 3, right? So remember, this means it does not say put in the 0 first and then take the derivative. It says do the derivative and then plug in 0, right? That's what this notation means. So we need to do 3 derivatives. Well, before I do any derivatives, let me make that a power. So what's the first derivative?
-2 times 1 -3.
And then times a -1.
Oh,
That's why I didn't write it.
God, you're so smart.
Thank you. What will the next one be? It is a -2, but the chain rule, there's another negative that pops out. When I take the derivative, the -2 comes down with this derivative, and this is -1.
So the -4.
Say it again.
6 times minus t.
Good. And then for third derivative,
24 minus t.
cool. And then now to find your expected value of x cubed. To find expected value of x cubed, what do we do? Plug in 0 for t into that third derivative, and you get 24. Notice if you already have the moment generating function, calculating these moments is a lot easier than actually going through and calculating the expected value of x squared or expected value of x or x cubed. So you can also use this, of course, to find the variance, because you can find expected value of x and expected value of x squared. So if I asked you for the variance here, that's our formula for variance, correct? Or that's a formula for variance. So if I want expected value of x squared, what is it? 6, right? Expected value of x squared is 6, isn't it? Using this one, m double prime is 0.
C.
So just to, I'll just write out the extra step. This is m double prime is 0 minus, oops, m prime is 0 squared. M double prime is 0 is 6. M prime is 0 is 2 squared. So we get 2. Right? Because we go back up here, plug in 0, we get 2.
Yes.
Does that make sense? Okay, I'm glad it was fun.
Now we don't have to do that all.
All right. So we'll do more of this next time, get into a couple of other distributions.
Oh. Ooh.
Have a good one. We'll see you. Yeah, Morgan.
So for the expected value of x, why don't we put that in?
Oh, sorry.
Why don't we get the first?
Send me in.
Like the expected value of x.
Because our, if I put in 0 into the first one, you don't want 0 into the first one. Just think about it as a definition. If I put 0 here, I get expected value of 1.
Oh, I know, I 100% knew it didn't work.
I get expected value of 1.
You did something wrong. You were sure for.
I don't want, expected value of 1 doesn't mean expected value of
They
x.
don't want to give me a new one, so.
Cheat.
You don't want to start.
What do you think?
Ashton, good luck tonight. I hope you win.
It's always one.
Thank you too.
Right? Right, if I put 0 in here, I get a constant, not a expected value of x.
What?
Which always
Chelsea, is
means
that what you want? Chelsea. What I sent you, is that what you were looking for?
well, that's what when the, because with the first derivative will give us the first moment, right?
Oh, I didn't see you
respond. I
respond.
want that n to be 1, so look into the first derivative.
The mean first.
The mean was the first one. Yep.
Sure, you sent us a I have to actually buy the text.
I'm sorry.
Just kidding. I have it.
Or you can borrow somebody's. I'm sure they probably have it.
No, I already have it, but I read it, so I have to read it.
Oh.
Then I'll see you at 4.
I'll be there. Oops.
Thank you.
Yeah, you're welcome. See ya.
I'm gonna go work on the first.